All right, guys, so this will be part 2. Hopefully it doesn't take too long here, okay? So we're just going to take what we did in the top section, and we're going to apply it to a different scenario here. And then in example 5, we're going to look at one of the more complicated equations, right? Or not equations, the series of like a product of a few different equations, okay, or functions, okay? And again, just to hit home the fact that you don't want to have to multiply and expand this all out just to apply power rule, okay? So let's find the equation of the normal line to the curve. And again, this is good review for, I don't know, the test that you're going to write today, right? It's if I ask you to find the equation of any line, right? It doesn't matter if it's normal. Normal just means perpendicular to the slope that we find. So let's derive this. And for the purposes of today's test, you would find the slope using first principles. Once you have that slope, you find the negative reciprocal. That would be the slope for the normal line. And then you just find the equation accordingly, okay? The exact same work. We're trying to make finding the derivative easier than using first principles, okay? So let's find the equation of the normal line to the curve this at x equals 1. So let's derive that. We could say, okay, well, dy dx is going to equal, we're going to derive the first one. Remember, this is f of x, and this is going to be g of x. So we take the derivative of f of x, that's going to be 3x squared minus 3. Multiply that against the original g of x function, 2x squared minus 5x. And then add the original f of x function, x cubed, so not very good, x cubed minus 3x plus 1, multiply that against the derivative of g of x, 4x minus 5. Okay, do the expansion work. Actually, you know what you could do? To make your life easier, you don't even have to do the expansion work here. If I give you the x value, just plug it in and do each number individually. Okay, and then do the multiplication at this point. You know, sometimes it's helpful to actually know what the equation of the tangent line is, at which point you could expand and clean it all up, and then you'd have one equation that represents all of the tangent lines around that curve. You know, all you would have to do is plug in specific x values. The problem with doing this, if we're only interested in this one x value, then you can plug it in. But if you know, we wanted a different x value, like let's say x equals 3, you'd have to plug it in again, and that may or may not be more work. I don't know. Okay, so let's evaluate here. If I were to plug in 3 times 1 squared, right, minus 3, that's all you're doing, right, all the way across. Right, we're plugging in the value of 1 for x. I may as well keep going now. Right, and then we're going to see 1 cubed minus 3 times 1 plus 1, 4 times 1 minus 5. Okay, and we're going to see 0 multiplied against negative 3 plus negative 1 times 1. Okay, and we find out that dy dx is actually going to equal 1 when x equals negative 1. Okay, and so that is the slope of the tangent when x equals negative 1. Okay, right there. That's the slope, m value. Now the problem is, when we're talking about a normal line, that's perpendicular, right? Normal means perpendicular, so I want m perpendicular. Well, the slope that's perpendicular to this value of 1 would be the negative reciprocal of that. Well, that's just negative 1. So that's m perpendicular. We have x, right? Remember, all I'm trying to do is create the equation of the line, mx plus b. You know x, you know m now. This is m perpendicular for the normal. and I want to find y. Or sorry, I want to find b ultimately. I still don't know why, but we can find it. If we were to plug x equals -1, well, it's not x equals -1, it's just 1. When I plug in x equals 1 into the equation, okay, I can find out that the x value, or sorry, the y value, if I were to do that, so when x equals 1, y will equal, remember, I'm just going to plug it into the original equation up here, right? Y would equal -1 multiplied by 3, -3, sorry. That's what happens when you you input the 1 value into, or the x equals 1 into both of those values, those functions, f of x, and then we see that the y value is going to be 3. So you know x, you know y, you know m perpendicular, you plug it in there, right? So we get 3 equals -1 multiplied by 1 plus b. So we get 3 equals -1 plus b, 4 equals b. So the equation of the line that represents, that is the normal to the tangent, right, perpendicular, would be equal to y equals -x plus 4. And if I wrote that in standard form, you would get x plus y minus 4 equals 0. Okay, and that's it, guys. That's the equation of the line. And I mean, you maybe should, I mean, this is my bad too, maybe. We should maybe state the fact that that is what it is. Okay, this is the equation okay, just be clear in what it is you've done, okay, on your summatives and things like that. Oh, you guys, oh no, we're okay. All right. So we have one final thing to do today, and it's what we call the extension of product rule. And it's what happens if I have 3, 4, 5 different kinds of functions, right, that are multiplied together in series, like in a series of products, right? And so we're going to need a way to tackle this. Well, it doesn't get much more complicated than the original product rule, right? We're still going to derive one of the functions, and then we're going to multiply by the other two. And then we're going to derive the next function and multiply by the original other two. And then finally derive the third function and multiply by the other original two. Okay, so that's what we're going to do. We're going to find dy dx, and we want to find the slope of the tangent at x equals 1. Okay, the nice thing is, right, when we do these questions and we give you, much like the first principles, right, if you're given a specific x value that you're interested in the slope, then it makes your life a little bit easier when you're provided an x value, because we're not going to have to do all this cleanup and expansion at the in like, I don't know, line 3 or 4, right? There is power in knowing exactly what the slope of the tangent is, right, for all points of x, right? There's power in knowing that. As you'll come to learn when we do the next unit on like rates of change and spend a little bit more time in like speeds and position and time graphs and things like that, right? And it's more powerful to have the actual derivative function in your hand so that you could find out any x value. Okay, and so there is there's a balancing act there, right? Where it's like, okay, as long as we know how to get the actual function, that's the important part. Okay, and then if we're only interested in one particular x value, then things are okay. Okay, so let's do the work here. We'll derive, you know, sometimes, again, easy to label, g of x, f of x, and h of x. And now we can just do the derivative, right? So we're going to say, well, okay, well, dy by dx, that's going to equal f prime of x. And again, I'm not looking at this. I'm trying not to look at it. I'm trying to write it out myself, right? F prime of x times g of x times h of x. And you guys are going to try and write this all out yourselves as well, right? And then you can say, well, you don't even need to flip around the order. You could just leave, okay, well, now I'm going to multiply by the original by g prime of x. So I'm just going to move which function I'm deriving, right? And then I'm going to add f of x, g of x, h prime of x. Okay, you'll notice I didn't necessarily follow this up here. I just moved the location of the derivative. Okay, and now we can go, okay, well, dy by dx, we're going to derive f of x, right? So the derivative of f of x is going to be just 2. 2 times the other two functions, right? X squared plus 1, x cubed minus x. Then I'm going to add. Well, what's f of x? F of x is 2x minus 3. Derive g of x, 2x. And then h of x is the original h of x function, h cubed minus x, plus f of x, again, 2x minus 3, x squared plus 1. And now we get to derive h of x, which is going to be 3x minus 1. Okay, this, I like this from the standpoint, okay, it's very clear. Here's this. Okay, and if I'm interested in x equals 1, then just plug in x equals 1 everywhere, right? And you can find out, you know, what the actual slope is. At x equals 1, you know, you could find out that we're going to get dy by dx is going to equal 2 times 2 times 0 plus 2 times negative 1 times 0 plus 2 times negative 1 times 2. So it looks like these terms are going to just wipe themselves out. It looks like I'm going to get dy by dx is going to equal negative 4. Okay, and so the value or the slope of the tangent is negative 4. The slope of the tangent for when x equals negative, just 1, negative 1. Okay, guys, that's it. Okay, I'd say the hardest part of this unit is going to be keeping track of when to use which law, and that's going to be it, right? All the stuff that we done in the first unit around finding equations of tangents, that's all going to come back and virtually the exact same as you can see here, right? In the last question where we found the normal, it's all going to come back in the exact same fashion, except we're going to find an easier way to find the derivative. Can you imagine? Can you imagine trying to use first principles to derive that? It'd be a disaster, right? You'd be there for days probably trying to derive that using first principles, right? That's not pleasant. Okay, and so we got to have ways to find derivatives more efficiently, and this is what they are, right? So we're going to spend this week looking at all the different, there's probably 5 or 6 different, much like factoring, different kinds of derivatives and when to apply them in different situations. Okay, that's going to be this week. And then finding equations using those slopes. Okay, and that's it, guys. Okay, so you guys let me know if you have any questions. Your summative will be out today as well. You guys can have a crack at that, and you guys let me know if you have any questions. Okay.